Welcome. In this video we look in Chapter 2 at two sections. I will treat briefly 2.4 on infinite limits and 2.5 limits at infinity. 2.4 infinite limits is about when a limit approaches a number like 3, but the y values shoot off either to positive infinity or negative infinity. In this case, in the first one that's pictured here, what's happening as x approaches 3? From the left, those y values grow without bound, and as x approaches 3 from the right, those y values also grow without bound. We would say that the limit, as x approaches 3, of f of x is infinity. I want to be really careful here. This is kind of a curious thing. The y values don't actually approach a particular number. So officially, the limit as x approaches 3 of f of x does not exist. But the limit does not exist in a very special way. It does not exist because all the y values are getting larger without bound. And so we write this equals infinity just as notation to express that idea. Similarly, how about a graph like this? As x approaches 3 from the left and as x approaches 3 from the right, the corresponding y values are getting lower and lower without bound. We would write the limit as x goes to 3 of f of x equals negative infinity. And finally, maybe they don't match up. Maybe as x goes to 3 from the left, those y values decrease without bound, and as x approaches 3 from the right, the y values increase without bound. And really, truly, in this situation, we just have to say the limit does not exist, and we can't put a positive or negative infinity there to express any kind of uniform direction. How about an analytic approach? So this is one without graphs. We just look at the symbols and kind of think about what's really going on. In this first example, x is approaching 7 from the right. So the numerator is approaching 17. And what's happening to that denominator, x minus 7? Well, it's approaching 0, but it doesn't ever quite reach 0. Does it stay positive or does it stay negative? And in fact, if x is approaching 7 from the right, my x values are a little bit bigger than 7. So that denominator is almost 0, but actually it's a small positive number. So I might write this as something like approximately 17 over approximately 0, but really positive. What kind of a number is this? Well, it's positive over positive, so this fraction is a positive number. But also, that denominator is tiny. And what happens to a fraction if it has a tiny denominator? The fraction is huge. So this denominator gets smaller and smaller and smaller while remaining positive, and so the fraction as a whole becomes larger up to positive infinity. How about that example again, but now I will approach 7 from the left. In this case, my x values are a little bit less than 7. So the denominator is still approaching 0, but since x's are less than 7, x minus 7 will be negative. So very, very close to 0, but actually a little bit negative. Now I have a positive over a negative, and positive divided by negative is negative. The denominator is tiny, which means the fraction is huge. It is a huge negative number. So this value becomes negative infinity as x approaches 7 from the left. Here's a picture of this situation, and you can see how this is reflected. When x approaches 7 from the right, the y values shoot off to positive infinity. When x approaches 7 from the left, those y values decrease down to negative infinity. How about an example like this? What's going on here? Well, the numerator stays 8, so that's good. In the denominator, x minus 2. So x is approaching 2 from the right. So that's 0. Well, I should say approximately 0. But it's just a little bit positive. And what about x minus 5? Oh, look at that. 2 minus 5 is negative 3. So it's approximately negative 3. So now I have positive over negative. So that'll go to negative infinity. And one last example. Same thing as above, but now I'm approaching 2 from the left. So the only difference is now this almost 0 in the bottom is negative. So it looks like I have positive on top, a negative times a negative on the bottom. So the whole thing is positive. So as a result, that limit is positive infinity. Vertical asymptotes occur where my limits shoot off to positive infinity or negative infinity, and we can figure out where they are by looking at the denominator. So in this case, my denominator had a 0 at x equals 2, and that's where the asymptote is. In this second example, there's a 0 at x equals 2, and also there's a 0 at x equals 4. And so 2 and 4, that's where the asymptotes occur. In general, the rule is that f of x over g of x has a vertical asymptote where that denominator is 0, but the numerator is not 0. Just take a quick look that in the first example, that numerator was not 0 when I plug in x equals 2, and in the right example, if I plugged in 2 or 4, that numerator was not 0. All right, moving on. How about limits at infinity? Now I'm going to let my x not approach a number, but I'm going to let my x values go off to positive infinity or negative infinity. This is the graph of the tan inverse of x. So it looks like as my x values get larger and larger, the value of the function approaches pi over 2. So as x gets larger, these y values are going up, and they're getting closer and closer and closer to the y value of pi over 2. And as x moves to the left, then the y values are decreasing, and they're getting really close to the y value of negative pi over 2. How about this one? What about the limit as x goes to infinity of cosine of x? Well, as x goes to infinity, what's happening to the y values? They go 1, negative 1, 1, negative 1, 1, negative 1. They oscillate forever, never really zeroing in on any particular y value, so that limit does not exist. What about a closely related function, cosine of x divided by x? Look, it still wiggles, but those wiggles are actually becoming shallower and shallower. As x gets really, really big, see that denominator, I'm dividing by a bigger and bigger number, but my cosine always remains between positive 1 and negative 1. So this fraction actually approaches 0. Now, sometimes we can combine infinite limits and limits at infinity. This is a graph of e to the x. So as x goes to infinity, what happens? As x goes to infinity, y goes to infinity also. What if x goes to negative infinity? Then the limit of the function is 0 as x goes to negative infinity. Here's an example. This is the natural log of x. What is the limit as x goes to infinity of the natural log of x? Can you see this? As x goes to infinity, those y values are increasing. In fact, they increase very slowly, but they will always increase. So in fact, that limit is infinity. Just a little bit of a change here. What if x goes to 0 from the right? X is approaching 0. What happens to those y values? Lower and lower and lower without bound. The limit of natural log of x as x goes to 0 from above is negative infinity. And our last example, x to the 5th. As x goes to infinity, the y values are also going to infinity. And as x goes to negative infinity, those corresponding y values are going to negative infinity. In fact, this last example is worth exploring a little bit. This is a power of x. So here are several powers of x. X squared, x cubed, x to the 4th, x to the 5th. And look at the graphs. It's shaped like a U, shaped like an S, shaped like a U, shaped like an S. So in general, if my n is even, that's the exponent. if the n is even, then as x goes to infinity, x to the n will be infinity, and as x goes to negative infinity, what'll happen? Oh, well, that's also positive infinity. These are my u's. X goes to infinity or negative infinity, those y's are always increasing. As x goes to infinity or negative infinity, those y's are increasing. All right, how about the odd powers? If n is odd, now I'm looking at x cubed and x to the fifth. As x goes to infinity, then x to the n approaches positive infinity. And as x goes to negative infinity, now here's where it changes. My x values fall forever. That limit is negative infinity. Well, now that we've established the behavior for these powers of x, let's broaden our view and look at polynomials. Here is a polynomial. So how will this behave, say, as x goes to infinity? And here's the rule. The end behavior of a polynomial function is the same as the end behavior of its leading term. So the leading term is that term that has the highest power of x together with its coefficient. So x to the 4, that's the highest power, and the coefficient is 5. So 5x to the 4, that's the leading term. So if I want to figure out the limit as x goes to negative infinity of the polynomial, all I need to do is take the limit as x goes to negative infinity of that leading term, 5x to the 4. So I know how x to the 4 behaves. That will go to infinity. So certainly 5x to the 4 also goes to infinity. Now how about this example? In this example, x goes to infinity, and here's my polynomial. What is the simple version? Limit as x goes to infinity. Well, my leading term, careful, it's not x, it's not 5x to the 10. The leading term is negative 3x to the 17. And now what happens as x goes to infinity? Well, x to the 17, so let me just write this down. Limit as x goes to infinity of x to the 17 is infinity. But if I throw a negative 3 in front there, that's going to negate that answer. So let's see, limit of negative 3x to the 17 equals negative infinity. And our last topic here, limits at infinity for rational functions. So first a quick note. If x goes to plus or minus infinity of something of the form a over b x to the n, the answer is going to be 0. Here's an example. The limit as x goes to infinity of, say, 2 over 7x to the 5th. And it's pretty easy to see why that answer should be 0, because look, the denominator is getting bigger and bigger and bigger and bigger. That numerator is just a constant. The numerator doesn't change. That's what the a is over here. The a is a constant. But that denominator gets bigger and bigger and bigger. And so the answer has to be 0. Even if I went to negative infinity, okay, so I'll erase this. What if I had put x goes to negative infinity? Well, still, that denominator is getting larger and larger in a negative sense, and so the whole fraction is negative, but the whole fraction still is getting closer and closer to 0. All right, so this gives us a way to compute the limit as x goes to infinity, or negative infinity, of a ratio of polynomials. And the trick is, find the ratio of the leading terms. So when I was looking at a polynomial, all I had to do was look at the leading term. If I'm looking at a rational function, a ratio of 2 polynomials, look at the ratio of the leading terms. So 3 examples. In all these examples, x goes to infinity. And see, in this first example, the leading term is, on top, the leading term is 6x squared. On the bottom, the leading term is 3x to the 7. So, limit as x goes to infinity of 6x squared over 3x to the 7. And that's the limit as x goes to infinity. Let's see, 6 over 3 is 2, but you know what? The larger exponent of x is in the denominator, so that's really like 2 over x to the 5th power. And now I can use my fact from above that if I have all my x's in the denominator, that limit is 0. Let's take a look at the second example. So in the numerator, the leading term is 5x to the 6. In the denominator, the leading term is 3x squared. I'll take the limit as x goes to infinity of that ratio, 5x to the 6 over 3x squared. In this case, the higher power of x is on top. And so I get the limit as x goes to infinity. 5 over 3 is 5/3. But now the x's I'm left with is just an x to the 4th. So this looks like my power of x, and it has a positive coefficient in front. Let's see, x to the 4 will go to infinity, so this whole limit is infinity. And then lastly, in my third example, I have a rational function. Let's see, the leading term of the numerator is that, the leading term of the denominator is that. So the limit as x goes to infinity of 6x to the 5 divided by 3x to the 5. Oh, and so that's the limit as x goes to infinity. Well, that fraction just ends up being 2, which is 2. So when the two exponents, or when the two powers of x are exactly the same, where that function ends up vertically is actually just at the ratio of those two coefficients. Alright, so we've talked about a lot with infinity and limits in this lesson. Be sure to let me know if you have any questions.